All right, here's our video, how Mercury's orbit baffled Newton, Isaac Newton, back in the late 1600s. So basically, and by the way, you're looking at this beautiful blue in Mercury, which really doesn't exist. It's just the computer models that were trying to highlight different variations on the planet. And those blue are crater rays. So if you looked at Mercury, you would just see a kind of a grayish landscape. And another interesting about Mercury, it is not the hottest planet, even though it is closest to the sun. It is the second hottest planet. Venus is hotter because of its runaway greenhouse effect. But another strange thing about Mercury is the other side of the planet is colder than Earth. So it's hotter and colder than Earth at the same time on one side. But anyway, getting back to its orbit. Now, according to Kepler, we know that planets orbit in an elliptical, not in a complete circle. And so Newton's laws of gravity, gravitation, and motion uh, were calculated based on that elliptical. So the problem here with Mercury is Mercury's orbit did not conform to the prediction of Newton's laws, and it baffled Newton and all the scientists of that day. And it actually took it took Albert Einstein to figure it out with his special theory of relativity. But we'll get into that. So let's get a clean page here. What should we use? Maybe we'll keep the red there. Who knows? And we'll draw a sun. Our sun's not red, but one day it'll become a red giant. Right now it's a yellow dwarf. And we'll put Mercury over there and attempt to draw an elliptical around the sun. So maybe that looks too much of like a circle. Let's do it better. Take two. Take two. All right, we'll put Mercury there. And we'll make more of an elliptical. There we go. There's the elliptical. So the closest point, and we'll have these vocabulary words now, the perihelion is the closest point. So let me write it down. The perihelion is the closest point of an object around the sun. So Earth has a perihelion also. And the closest point for Earth is actually in the winter time in the northern hemisphere. So the perihelion is the closest point. And the furthest point, put over here, is the aphelion. Sounds like some Greek myth. So we'll concentrate on the perihelion. So according to Newton's laws, the perihelion should stay fixed over time with Mercury. It shouldn't change, but Mercury's does. So in other words, the gravitational force between the sun and Mercury should stabilize because of this elliptical orbit. It should stabilize the perihelion. But that was not happening, and it baffled Newton. And by the way, so we're looking at the closest point of around 29 million miles to the sun, and the furthest point looking about 43 million. And we're in miles here, talking miles. But on Earth, remember on Earth, for Earth itself, we're 93 million miles on average away from the sun. All right. Of course, in science, and what Newton would have used is kilometers. So 29 million miles, make sure we put miles there, would be about 46, or close to 47 kilometers. Well, we should say 46 million kilometers. And over here, we say 43 million miles, and that's about 69 million kilometers. So again, when Newton did his calculations, and we'll show some of those calculations, he would have used kilometers. So again, the problem with Mercury is the perihelion wasn't in a fixed location, and it just wasn't adding up, so to speak, with his laws of gravitation and motion. So he hypothesized, like all scientists would do, that Venus and Earth and Jupiter and maybe other orbs out there were pulling on Mercury. But when he did the calculations on it, that didn't add up either. So it baffled him. It baffled him and other scientists when he looked at this in the 1680s, and he died in 1720 without an answer. And again, like I said earlier, it took Einstein the theory of relativity to solve that, and with something called space-time curvature. So let's write that down. Space-time curvature. Basically, space is curved. Gravity will bend space. Let's look at a picture. All right, so here's the sun in a bending, curving space. It has like a sun well, if you want to speak. And we can put Mercury. Let's put Mercury over here. A little dot over there. So the space-time curvature is the sun causes space-time to curve, especially as Mercury gets closer and closer to the sun. So it'll kind of dip into this well, so to speak, as Mercury gets closer to the sun and moves out of the well. It's like moving into a well. So again, as Mercury moves toward its perihelion, the closest point, it gets deeper into this gravity well, the sun's gravity well. You can imagine if you had a bigger sun like Betelgeuse or Betelgeuse, whoever you want to pronounce it, how much that gravity well would be. And if you want to go further, imagine what a black hole's gravity well would be. It'd be infinite. So we'll look at the formulas that Newton would have looked at and found that he was having a problem with. The first was, now Newton came up with the gravitational force, the universal gravitational force. And he came up with this formula, and we'll put it as F in Newton's, will be the gravitational force G times the mass of, like the sun, for example, or the mass of the other orb, in this case Mercury, all divided by R2. And R is the distance between, in this case, Sun and Mercury. That would be R. So that would be one formula he had to work out. He also had to work out acceleration. And he had to work out velocity. He had to go through all these processes. So according to his second law, right, we have F equals m times acceleration, mass times acceleration. And if you just, you can manipulate the problem here, you can have acceleration equals force divided by mass. So he had to come up with that problem. And then he had to come up with velocity, and velocity is F equals mass times velocity squared, all over R, again, the distance. And remember, acceleration is the change of velocity over time. So we needed to know the change of velocity over time. And we can manipulate this, put a little arrow down and manipulate this formula. Just multiply R with F. So you have F and R. You can multiply up over there. And then you get m times velocity squared. Remember, you're trying to isolate the v, so divide m out on both sides. Doing a little fancy math here. And F over R over m equals v squared, but we don't want v squared, we want v. So need to know a little algebra here. You just square root both sides, and if you know algebra 1, you know what I'm doing here. And then we get our equation finally of velocity is the square root of Fr over m. So these are the three equations he would have used. You can plug these in, finding the mass of the sun, the mass of Mercury in this case, and the distance between them. They plug them in. And of course, you would have had a prediction of where Mercury should be in its orbit. And of course, that wasn't working out for Newton. As Isaac Newton, I said that twice already. As Albert Einstein figured out, it was the space-time curvature, because the sun is actually curving space, and that's what was this discrepancy that Isaac Newton couldn't figure out, and perhaps he would if he had more time. All right, that's our video today.